Alright, so we proved this Zalcman's lemma in the last lecture, and you know, basically it's a theorem and it is a characterization of normal families. And I also remarked that you know, at the end of the lecture I remarked that the converse of Zalcman's lemma is also true. Therefore, Zalcman's lemma is a characterization of you know, non-normal families. Okay, and it is like and you know, it's like Marty's theorem. Marty's theorem is a characterization of normal families of meromorphic functions, and Zalcman's lemma is a characterization of non-normal families. Okay, and both of them are very important in the when you go to the proof of the Picard theorems, which is our main aim. Okay, so I just want to begin with the following remark. So recall that you know, when I was giving you the motivation for Zalcman's lemma, we actually proved this result. So if you take a family script f of meromorphic functions defined on a domain in the complex plane or even in the extended plane, and you take a point z0 in the domain where the family is normal, okay, then you give then this normality at a point, which is supposed to be normality in some neighborhood of the point. So normality at a point is defined just like analyticity at a point is defined. Okay, so normality at a point means normality in some open disk surrounding that point. Okay, and if you have a family which is normal at a point, then it has this property that, you know, given any sequence of points tending to that point, Zn tending to Z0, and a sequence of decreasing positive radii, a sequence of radii tending to 0, okay, then give me any sequence in the family, I can find a subsequence such that the zoomed functions converge normally to a constant function on the plane. Okay, this is what we proved, and this was very easy to deduce. Okay, and Zalcman's lemma actually tells you that if the family is not normal, you will get the exact opposite, namely you will be able to find a sequence such that the zoomed functions converge to a non-constant meromorphic function. Okay, that is the big difference. Okay, and what I want to tell you is that the converse of this proposition is also true. If you apply, it's an exercise which you might, for example, do. You'll have to use a diagonalization argument. Okay, and you can do this simple exercise, and well, not so simple but not so hard also, but you can use Zalcman's lemma and show that the converse of this proposition is true. Okay, so I'll write that down first. So so here is a theorem. So here is again a proposition. This is converse of the proposition stated before Zalcman's lemma, and what is this proposition? Well, it's a criterion for normality. So suppose script f is a family of meromorphic functions on a neighborhood of a point Z0. Okay, the point Z0 could be a point in the extended plane, really it could even be the point at infinity, it does not matter. Okay, suppose that for every sequence Zn tending to Z0 and every sequence epsilon n tending to 0 plus epsilon n are all positive numbers. Okay, so given any sequence Fn in the family script f, there exists a subsequence fnk such that the zoomed sequence so what is the zoom sequence? It is g n k of zeta is the zooming of f n k at zk with the zooming factor 1 by epsilon k and using the variable zeta, and this is just f n k is z of zk plus epsilon k times zeta. Okay. So this zoom sequence converges normally on the complex plane to a constant value in, so this constant value can also be the point the value infinity, so it is a constant value in the extended plane. Okay. So suppose this property is satisfied by the family script f, okay, that whenever you give me a sequence of points converging to z0 and a sequence of radii going to 0, from any sequence fn I can extract a subsequence for which the zoom sequence converges normally to a constant, okay. Then script f has to be normal at z0, okay. Then script f has to be normal at z0. That means it has to be normal in some open neighborhood of z0, okay. And I won't write down the details, but I leave it as an exercise to you. Proof is use Zalcman's lemma and a diagonalization argument assuming assuming the family script f is not normal, on a decreasing sequence of neighborhoods of z0. So I'll just this is actually more of this is an exercise, okay. This is an exercise that I want you to do. So the proof is by contradiction, okay. So you assume I have to show that this family is normal at z0, which means I have to show that the family is normal in some open neighborhood of z0. So if that's not true, it means that in every open neighborhood of z0 the family is not normal. So you take a decreasing sequence of open neighborhoods of z0, okay, the neighborhoods becoming smaller and smaller. For example, you can take a decreasing sequence of open disks centered at z0 with radii 1 by n where n goes to infinity, okay. And on each of these disks you can apply Zalcman's lemma, because Zalcman's lemma applies to a non-normal family, okay. And then you will get sequences from the Zalcman's lemma, and then you apply the right diagonal, you apply a diagonalization argument and then apply the hypothesis of the proposition and you will get a contradiction, okay. So I leave it to you to do that, right. So so now let me continue with the main result. The main result is, well, you know, what we are going to, which is going to be the main, one should say this is really the deep theorem, that is the theorem of Montel, okay, and it's a theorem on normality, okay, and it's a deep theorem because it involves lots of things. It involves several theorems in complex analysis, and it is the key to proving the Picard theorems, okay. So the point is that so this is the Montel theorem. And what is the Montel theorem? The Montel theorem, it's a it's actually it's a normality, it's a theorem for normality of a family, and what it says is that you take a family of meromorphic functions on a domain, okay. If you know that the functions in the family always omit 3 values in the extended plane, 3 distinct values in the extended plane, then the family is normal, okay. So it's a beautiful theorem. To check that a family is normal, all you make sure is that you find 3 values in the extended plane, which means you have to find 2 complex finite values in the complex plane, the finite complex plane, and 1 probably the value infinity, okay. So you should somehow find 3 values that all the functions in the family miss, okay, and they should omit these values, and if you do that, then you can then the theorem says that the family is normal, okay. So somehow omission of values is connected to normality, okay. The normality of the family is connected to omission of certain number of values by functions in the family, okay, and the theorem says that if you can make sure that the family omits 3 values, then you are sure it's normal, okay. And mind you, normality is a condition for compactness, okay. So you can imagine the theorem is very powerful. You are saying that a certain family of meromorphic functions on a domain, you are saying that it is compact in the sense that it's normally sequentially compact, that is every sequence admits a normally convergent subsequence, okay. That's a very strong property, okay, and to deduce that, all you need to say, you have to just verify that the family omits 3 values, okay, three values, and it's really beautiful. So so in particular what it means is that if you take a family of analytic functions on a domain, okay, if you take a family of analytic functions on a domain, okay, and if you know that it omits 2 finite complex values, okay, then you can immediately say that it is normal, okay, because when you are looking at analytic functions, you can forget the 3rd value, which is infinity, okay, infinity is already omitted, okay. So this version of the theorem, Montel theorem, is called the fundamental normality test, okay. So if you want to check a family of analytic functions is normal, okay, on a domain, all you have to do is you make sure that it omits, make sure that every member of the family omits 2 fixed complex values, okay, and then you are sure that it is normal, okay. So it's a very deep theorem, so let me state it. So this is Montel's theorem on normality. So here is the theorem. Let script f be a family of meromorphic functions on a domain D in the extended complex plane such that script f omits 3 distinct values in C union infinity. So what does this mean? That is, there are elements lambda 1, lambda 2, lambda 3 in C union infinity, and of course they are all distinct, lambda I not equal to lambda j for I not equal to j, okay, such that each such that for each f in the family, f does not take the values, any of the values lambda 1, lambda 2, lambda 3, okay, these are omitted values, then script f is normal. So this is the I mean the deepest, I would say this is the deepest theorem in this course. Okay, this is the most important theorem in this course. All right, to check that a family of meromorphic functions on a domain is normal, you just ensure that it omits 3 values. All the functions in the family omit three fixed values. Okay, 3 distinct fixed values. All right, so so here is so how do we go about the proof? So the first thing I want to tell you is that you know a fundamental property of Mobius transformations, that given any 3 values in the extended plane, you can find a Mobius transformation that can map those 3 values to 0, 1 and infinity. Okay, so you can always I mean this is the way in which you write down a Mobius transformation in terms of cross ratios, because a Mobius transformation has a fundamental property that it preserves cross ratios. So this is something that you should have seen in a first course in complex analysis. So these 3 values lambda 1, lambda 2 and lambda 3 in the extended plane, I can apply a Mobius transformation and make those map those values to 0, 1 and infinity. Okay, and then I can compose the whole family by this, I can transform the family using this Mobius transformation. I transform the whole family by using this Mobius transformation, and therefore without loss of generality, by using a Mobius transformation I can assume that the values that are omitted, the 3 distinct values that are omitted are 0, 1 and infinity. Okay, so this is the first reduction, right? So let me write this down. Using a Mobius transformation we may assume without loss of generality that lambda 1 is 0, lambda 2 is 1, lambda 3 is equal to infinity. Okay, you can do this, right? So so you can assume, and of course by Mobius transformation I mean bilinear transformation or linear fractional transformation. Okay, so that's the first thing. Then the second thing is that the domain on which the domain D in the extended plane where this family is defined, okay, that domain also can be you can change that domain and scale it so that it contains the unit disk. Okay, okay. So the point is that see, I'm trying. What am I trying to check? I'm trying to check that this family is normal. My final aim is to check the family is normal. But how do I check its normal? I check its normal by checking its normal at every point, because normality at a point means normality in a small open disks containing that point, and the property of being normal is a local property. So if you check it at every point, that is if you check it in an open neighborhood of every point, that's enough to check it is normal on the whole domain. Okay, so it's like checking analyticity. You don't have to check if you want to check a function is analytic on a whole domain, it's enough to check at every point of the domain it is analytic. So what I will have to do is I can assume that I am checking normality of the family on a small disk, on a domain which is like a disk. Okay, and of course if I am checking at the point at infinity, all right, then I will have to take a neighborhood of infinity which is exterior of a disk in the complex plane, and I will have to change the variable from z to 1 by z to make it into a disk surrounding the origin. So in any case I can always assume that I am checking normality on a disk in the complex plane, and I can translate that disk to the origin and scale it so that it contains the disk contains the unit disk. Okay, so again this is another reduction I am making. Without loss of generality, it's enough for me to check that the family is defined on the unit disk. Okay. So this is another reduction. Okay. Without loss of generality, we may assume that D contains the unit disk mod z less than 1, okay, because basically because you have to check normality locally, and that means you have to check normality on a disk surrounding every point, and that disk I can assume it to be the unit disk, okay, because I can always translate any small disk to the origin, okay, so that the center of the small disk goes to the origin, and then I can scale it so that it's big enough so that it contains the unit disk, okay, and translations and scalings are also Mobius transformations, so they are not going to modify the properties of the family, okay. So so my situation is like this. I now have a family of meromorphic functions, okay, I now have a family of meromorphic functions defined on the unit disk, and what is given to me is that they omit the values 0, 1 and infinity. I have to check that the family is normal, okay, but look at the beauty of it. Since these functions omit the value infinity, they are analytic, okay, because a meromorphic function takes the value infinity only at a pole, and the moment you assume that it does not take the value infinity, all the functions have become analytic, alright. And the other thing is that all the functions are non-vanishing also, because the value 0 is omitted, okay. So you are having non-vanishing analytic functions on the unit disk, okay, and they all omit the what is the nice thing? The nice thing now is that if you have a non-vanishing analytic function on a simply connected domain, you can always find kth roots, okay, which are analytic, okay, because the reason is if you have a non-vanishing analytic function on a simply connected domain, you can find a logarithm for the function, and once you find a logarithm, multiplying that analytic logarithm by 1 by k and then taking exponential, okay, so e power 1 by k log will give you a kth root of the function which is analytic. So the advantage now is that your family has kth roots, every function in your family has kth roots for all k, okay, and the trick is what the point is that since the see if a function does not take the value 1, okay, then its kth root cannot take the value which is equal to a kth root of unity. If the original function does not take a value 1, then its kth root cannot, the analytic kth root cannot take a kth root of unity as a value, okay, and what case we will be using? We will be using 2 power case, okay. So I am going to write that down. Note that script f is analytic and non-vanishing on mod z less than 1, which is simply connected. So the so the families, so I will put this as f sub k, this is f to the 1 by 2 to the k, where f is in script f, are defined and analytic on the unit disk with omission of the values 0, infinity and 1 by 2 to the k, which are 2 power kth roots of unity. Okay. So you see this, mind you, the whole point is f to the 1 by 2 power k is defined as e to the 1 by 2 to the k log f, and this log f, an analytic branch of log f, exists because the domain is the unit disk is simply connected and f never vanishes on the domain. Okay. So this is something that is very, very important. Okay. So fine, and you know, see, now you but where now, you know, I want you to understand what the idea is. See, the idea is, you know, these so you look at these functions. Okay. These functions are defined on the unit disk. Okay. But then, you know, what I am trying to prove that they are all normal. I am trying to prove that this family script f is normal on the unit disk. Okay. And mind you, that means that I can extract, the normality is just that I can extract from any sequence a normally convergent subsequence. Okay. But you see, if I can extract such a from a sequence a normally convergent subsequence, I can do that also for the 2 power kth roots. Okay. So it's obvious that, you know, the family script f is normal if and only if any of the family's script f sub k is normal for any k greater than 1. Okay. So actually it amounts to showing that f is normal. It's enough to show that one of these script f k's is normal. Okay. And therefore if you contradict the normality of script f, what happens is you are contradicting in one stroke the normalities of each of the script f sub k's. Okay. And once you contradict the normality of each of the script f sub k's, Zalcman's lemma comes into the picture and gives you a zoomed limit function, which is a non-constant meromorphic function on C with spherical derivative equal to 1 at the origin, and the spherical derivative is always bounded by 1. Okay. And the beautiful thing is that function that you get is an entire function. Okay. Because it is a limit of functions from each of these families. It will not take the value infinity, so it will be analytic, and it will be defined on the whole complex plane, so it will be entire. Okay. And then you will see that you can get a contradiction easily by applying Liouville's theorem. Okay. So so let me write this down. Note that f is normal if and only if fk is normal for every k or for some k. Okay. So so we are going to proceed by contradiction. What we will do is assume script f is not normal. Okay. Because we would like to use Zalcman's lemma, which is a characterization of non-normality. All right. So assume f is not normal. Thus f sub k is not normal for every k. All right. And Zalcman's lemma gives for each script fk a zoomed limit function I will call the zoomed limit function as g sub k of zeta, okay, on the whole complex plane, which is meromorphic, non-constant, its spherical derivative at the origin is 1 and all its spherical derivatives are bounded by 1. Okay. This is what Zalcman's lemma tells you. See, Zalcman's lemma tells you that whenever a family is not normal, I can get a zoomed limit function which is non-constant meromorphic, and the non-constancy is kind of normalized or fixed by making the spherical derivative to be 1 at the origin. And mind you, the limit function is defined as a function on the whole plane. Okay, the zoomed limit function is on the whole plane. So I have this. Okay, now what I want you to notice is that the first thing I want to tell you is that the zoomed limit function, what is each zoomed limit function? It's a normal limit of meromorphic functions. Okay, but it's a normal limit of functions from fk, script f sub k, but mind you, script f sub k are all analytic. Okay, see, because we cleverly assumed one of the omitted values is infinity, and therefore we are only working with analytic functions. Okay, therefore this limit function, these limit functions gk's, they also have to omit the value infinity. The only other possibility is that they can be identically infinity, because whenever you have a normal limit of analytic functions, okay, then either the normal limit is again the limit function is again analytic, or it is identically infinity. This is the only thing that is possible. So the only thing that could have happened is that these limit functions are all identically infinite. Some of the limit functions, zoomed limit functions gk's, they could have been identically infinity, but but even that cannot happen, because if they were identically infinity, the spherical derivative would have been 0. But I have put the condition that the Zalcman's lemma tells you that the spherical derivative at the origin is 1. They are non-constant. So what it means is that all these gk's are all entire. They are all entire functions. You have cooked up a family of entire functions. You have cooked up a sequence of entire functions. Okay. So let me write that down. Note that since gk hash of 0 is 1 and gk is a normal limit of analytic functions from the family fk, gk is entire. It's entire because it is analytic and it is defined on the whole plane, so it's entire. And the point is that it doesn't take the value infinity. It cannot take the value infinity. See, in principle it could have been a meromorphic function. It could have taken the value infinity at a pole, but it can never take the value. The only way, the only possibility is that because it is a normal limit not of just meromorphic functions, but it is a normal limit of analytic functions. Okay, the limit can only either be completely analytic or it can be completely identically infinity. You cannot get from a limit of normal limit of analytic functions, you cannot cook up a meromorphic function. This will not happen. That is basically because of Hurwitz's theorem. Because if you cook up a meromorphic function, it means that your pole is popping up in the limit. But if a pole pops up, then for the reciprocal function a 0 pops up. Hurwitz's theorem says that a 0 of the limit will come from the 0 of the original functions beyond a certain stage. That means the original functions, the reciprocals of the original functions, if the limit takes if the limit takes value 0, or if the limit takes the value infinity, okay, then the reciprocal of the limit will take the value 0, and the reciprocals of the original functions beyond a certain stage should have zeros, which means that beyond a certain stage the original functions should be meromorphic, but they are all analytic. Okay, so basically it's Hurwitz's theorem which is working behind all this. So therefore each of these functions is entire, and the beautiful thing is what are the values that they miss. See, this gk will miss the value 0, infinity of course, and all the 2kth roots of unity. because every function in fk, script fk, is supposed, by construction it misses all the 2kth roots of unity. Okay, so let me write that down. Note that gk misses the value 0 and infinity 0 and the 2kth roots of unity. Okay, and actually what I am using here is actually Hurwitz's theorem. Use Hurwitz's theorem. Okay, so again let me repeat that. What does Hurwitz's theorem says? Say you take a sequence of analytic functions. Okay, suppose it converges normally to a limit function. Okay, a normal limit of analytic functions is always analytic. Okay, or it can be identically infinity, but this being identically infinity is anyway out of the picture because all the spherical derivatives are all non-zero. Okay, so the limit is always an analytic function. Okay, so if you have a sequence of analytic functions that converge normally to an analytic function, then the limit function, if it has a 0, then the 0 must come by a limit of zeros of the original functions that are converging beyond a certain stage. That is Hurwitz's theorem. Okay, in other words, what are you saying? What is it saying? It's saying that, if the limit function takes the value 0, then the original function should also take the value 0 beyond a certain stage in a neighborhood of the 0 of the limit function. Okay, and this is not only true for the value 0, it is true for any value, because the for f of z to take the value lambda, it is the same as looking at a 0 of f of z minus lambda, which is also analytic. Okay, so actually what you can say is the Hurwitz's theorem can also be thought of as, suppose you have a sequence of analytic functions, suppose it is converging normally to a non-constant analytic function. Okay, then if the limit function takes any complex value, then all the original functions also should take that complex value beyond a certain stage. That is what it says. And in fact, Hurwitz's theorem says more. In fact, it says that even the multiplicities should coincide. The multiplicity, if the limit function takes a value with a certain multiplicity, then all the functions in the original sequence that converge to that limit function, they also should take the same value with the same multiplicity beyond a certain stage. Okay, in a neighborhood of the point where that value is assumed. Okay, so this is just Hurwitz's theorem. Okay, so mind you, the spherical derivative is a non-negative real valued function. Okay, the limit function gk, these are all these are the ones that are entire, and they miss the values infinity 0 and the 2k roots of unity. Okay, and of course I will have to make use of these two conditions here, that that they all have spherical derivative 1 at 0 and they all have spherical derivative bounded by 1. So note that all these gk's having spherical derivative bounded by 1, what does it tell you? You can apply Marty's theorem now. You look at the sequence of gk's. This is a sequence of entire functions on the plane. Okay, gk is a sequence of entire functions on the plane. Their spherical derivatives are all bounded. Therefore, by Marty's theorem, there is a subsequence which will converge normally on the plane. Okay, so now I am applying Marty's theorem. Okay, by Marty's theorem, this gk has a convergent subsequence, normally convergent subsequence. G and k on, of course, it's normally convergent on the whole plane. Okay, because gk is of course it's a family of entire functions. Okay, let's take take such a normally convergent subsequence and take a limit. take the limit function, okay, you will get a function g, all right. Now that function g, see that function g is now a normal limit of entire functions, okay. Therefore the only possibility is that it is also entire, okay, or it is identically infinity, but it cannot be identically infinity because of the spherical derivative being 1 at 0. So the limit function is also going to be an entire function, okay, and you will see that is the function for which I am going to apply Liouville's theorem and get constancy, which is a contradiction, okay. So let g be limit as k tends to infinity of g and k, okay, then g is entire, then of course g hash is also bounded by 1 and g hash at the origin is 1, so g is entire non-constant and non-constant, okay. So you have cooked up an entire non-constant function, okay, and see now comes something very nice. See each of the g and k's, the values that they omit are 0, infinity, and the 2kth 2 to the nkth roots of unity, okay. But as k becomes large, these 2 to the nkth roots of unity, they, if you take the union of all these, that is a dense subset of the unit circle, okay. So what it means is that this g, this function g, it omits a dense subset of values of the unit circle, therefore it has to omit all values on the unit circle. This is because of the open mapping theorem. What does the open mapping theorem say? Whenever a function takes a value, it has to take all values in a small disk surrounding that. The image of every open set is an open set. For a non-constant analytic function, the image of an open set is always an open set, okay. So g being an entire non-constant entire function, if g omits values on a dense subset of the unit circle, by the open mapping theorem g has to omit all the values on the unit circle, okay. But the unit circle disconnects the plane into two pieces, one is the interior and the other is the exterior, and therefore the image of the complex plane under g, which has to be connected, has to either go completely inside the unit disk or it has to go completely outside the unit disk. If it goes inside the unit disk, then you have found g is a bounded entire function, so it is a constant, that is a contradiction. If it goes completely outside the unit disk, you take 1 by g, which is also going to be entire, because mind you g also omits the value 0, so 1 by g is also entire. So 1 by g will become a bounded entire function, it will become constant, therefore g will become a constant. So in any case you get g is a constant, you get a contradiction, okay, and that proves the theorem, that is all, okay. So what you must appreciate is you have used open mapping theorem, you have used Hurwitz's theorem, you have used Zalcman's lemma, you have used Marty's theorem, okay, everything has been used, okay. So let me write this down. Since gk, so g to the nk omits the values 0, infinity, and 1 by 2 to the nk, g omits the values 0, infinity, and mod z is equal to 1 because of the open mapping theorem, which says G is open and the fact that 1 by the 2 power nkth roots of unity k equal to 1, 2 and so on is a dense subset of mod z is equal to 1. Okay. Thus, G of C which is connected and belongs to complex plane minus mod z is equal to 1 has to imply either mod g is less than 1 or mod g is greater than 1. Okay. If mod g is less than 1, Liouville's theorem implies g is equal to constant, contradiction. It is not constant because spherical derivative at the origin is 1, okay. And if g is if mod g is greater than 1, then 1 by g is entire and mod 1 by g is less than 1. So again Liouville's theorem implies 1 by g is constant, which implies g is constant, again contradiction. Okay. So that is it. So the family has to be normal, right. So that finishes the proof of this theorem. And as a corollary, you can see that if you have a family of analytic functions on a domain, if you know that the family omits two complex values, two finite complex values, then it has to be normal. That is a corollary of this. Okay. This theorem that we have proved is for meromorphic functions, and you are including the value infinity also. Okay. So sometimes that is called as if this condition of omitting 3 values being omitted for a family of meromorphic functions or 2 values being omitted for a family of analytic functions is called the fundamental normality criterion. So it is a condition, very simple condition to check whether a given family is normal. Okay. I will stop here.